Nice. Okay. So my name is Yujian Tang. If I look familiar, it's because I'm usually hosting these events. And today I'm going to be talking to you about the key to scaling LLM applications. Who here knows what an LLM is? Please raise your hand. Great. Who wants to tell me what that stands for? Anybody? Okay, you right there. Here, you're going to get a sock. I have 9 more socks to give out. So be ready. So a little bit about me. My name is Yujian Tang, as I just said. I'm a developer advocate at Zillas. If you have not heard of Zillas, we are the maintainers of an open source vector database. And I'm going to be talking about vector databases as part of the key to scaling large language model applications. And Zillas, if you guys are curious, the name stands for zillions on zillions. I asked when I joined, I was like, where did you guys get this name? But it's because Milvus is the vector database for enterprise scale applications, and we're built to handle billions of vectors because it is a distributed system native architecture. And this QR code, by the way, is my LinkedIn if you want to connect, and those are also other ways that you can reach me. It says something went wrong. Wow. I will have to change that for next time, but for now, you can just search me up on Google because no one else has this name. So before we get started, I'm going to talk a little bit about Zillas. I work here, or I work there. You can find us on Twitter, LinkedIn, and Milvus is the Slack channel. So we maintain an open source application. So, we have a Slack channel for the open source one. And also we have a GitHub that's github.com/milvus-io/milvus that is the vector database. And once again, is open source. So I think someone back there was looking to contribute to an open source application. And if you are, check it out. And if you like what we're doing, give us a start. Okay, so let's get into it. Today, I'm going to be splitting my talk into 5 pieces. So first, we're going to talk a little bit about large language models. I'm going to give you a little bit of history of how neural networks got to this point. And then we're going to talk about some of the challenges with LLMs. As you know, these are really hyped up, but nothing is perfect. And as the solution to some of these challenges, I'm going to introduce the CVP framework. And CVP stands for ChatGPT. Who can guess what the V stands for? Okay, I think you were the first one to say it. Okay, who wants to guess what P stands for? It's going to be prompt as code. I'm sorry, nobody gets this one. And then I'm going to cover what a vector database is. If you know what a vector database is, that's great. I'm going to cover it anyway. And then we're going to go over a quick demo if we have time. So recently there's been an increase in large language models, and they've really gotten crazy. Like everybody has heard of them. Everybody's heard of ChatGPT. The first logo is OpenAI. These are a couple other LLMs, Claude and Bard Experiment. Does anybody want to tell me who made Claude? There you go. Okay, so a little bit of history. Let's go back about 10 years, 10, 15 years, timelines, right? 10, 15 years ago, we were really introduced to the popularization of convolutions through computer vision. So convolutions are these tricks, techniques, whatever you want to call them, that gives you context into the local window. So it gives you context into the tokens that are around you. So for example, if I have this sentence, Milvus is the world's most popular open source vector, well, it's vector database, but vector, there's no database on the slide. You would see that some of these words have context, or they get input from some of the words around them. For example, world gets input from the, and the and get input from world. Moving on from convolutions, we have this thing called self-attention. And so self-attention is a network architecture that gives you global context. And so what this means is that every word in the sentence knows about every other word in the sentence. So in the sentence example, Milvus is the world's most popular vector database. Milvus would have context of all of the words behind it, and vector database would have context of all the words before it. And that gets us to where we are today, or at least what generative AI kind of does, which is causal attention. So causal attention is where you have directional global context in a way that makes sense. So words that come later have context of the words that come before them. So in the example, Milvus is the world's most popular vector database. Milvus would not have context of the words vector database, but vector database would have context of the word Milvus. Okay, so what does all this lead to? This all leads to this thing called prediction. So LLMs are these stochastic models, and what that really means is that they have no understanding of what they're saying, and what they do is they predict on the input data that they've been given. So they predict future tokens, and once again, I'm going to go back to the same example. Milvus is the world's most popular vector, blank, and now you know why I didn't have database in the first slide. It's going to predict a series of possible tokens, and these tokens could be database, search, such as, like in the case of vector search engines, embedding, in the case of vector embeddings, which I'm going to talk about a little later, or some other set of words that I didn't put down here. And the correct case, or what the LLM would pick in this case, would be database, because database has the highest probability. So what's the downside of this? Downside is that the outdated input data could be cause for hallucination, and a hallucination is a plausible sounding but factually incorrect response. So an example of this would be, for example, Milvus is a type of mammal. Sounds like it could be, right? It's an animal. Milvus is actually a type of bird. It is a medium to small sized bird of prey, for those of you who didn't know. Okay, so I'm going to walk through a little bit of math because we are this is a tech talk, and you guys are all techies, so I assume you guys have some idea of how math works. And the mathematical representation or formulation of this stochastic model of an LLM is basically given some number of tokens from T0, T1, blah, 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 Tn, predict Tn plus 1. So who remembers Bayesian probability? Okay, yeah, I'm not getting any socks for this one, sorry. So this is basically an example of Bayesian inference, right? What is the probability of database given Milvus is the da-da-da-da-da? Or what is the probability of search given Milvus is the da-da-da-da-da? And so that's basically all this is showing you the mathematical formulation of what I just said earlier, which is that LLMs try to predict the future tokens. Okay, now let's look at some of the challenges with LLMs. Before I dive into this, does anybody have an example of an LLM hallucination they would like to share? Has anybody worked with GPT and has found any challenges? There's a sock for this one. Hey, Raja.
So ask it to generate a bio for you and see what you get.
Okay.
Fantastic hallucination.
I bet you would come up with something random. So I don't know if I can throw this all the way back there, but I'm going to try.
I need you.
Got halfway. All right, thank you. All right, so let's look into some of these challenges, right? So I'm going to give you an example of a hallucination, but before I dive into this, I'll just give you two of the most common types of hallucinations that GPT does. So number one, GPT does not have up-to-date information. Since it has been trained, the most up-to-date information it has is from 2021. And as you guys know, we are now in 2023, so it's like a year and a half out of date. And it also doesn't have domain-specific knowledge. So for example, like Raja was saying earlier, if you ask it to generate a personal bio for you, chances are it has no idea how to do that. But we're going to look at the example of how do I perform a query using Milvus. Okay, so this is the response that ChatGPT generates. And you don't actually have to know any code for this. Don't worry about it. I'm actually going to go to the next slide to show you what you should look at, which is it says that you want to import this Milvus library, or Milvus function client, whatever, from the Milvus library. And then you want to connect to it using this code, formulation, whatever. And this is actually not how you connect to the Milvus library. There's actually an SDK in Python called iNotice, and you connect through this thing called connections, and you call connections.connect, blah, 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 blah. And I'll show you that later. But I just want to point out, this is the example that ChatGPT gives, and it's wrong. And later in OSS, I'm going to show you another example from ChatGPT and an example from an application that we built that has domain-specific knowledge. So the solution to these hallucinations, at least in the case of domain specificity, is inject domain knowledge into your large language models. And that is where the CVP framework comes in. So before I cover exactly how the CVT framework solves this hallucination issue, I'm going to talk a little bit about what the CVP framework is. The main idea is that we can view these LLM applications as a general purpose computer. And in a computer, you have multiple things, and namely the three things that we want to point out that you have in a computer are a processor, persistent storage, and code. And so in this case, ChatGPT or any other LLM that you would like to use is the processor, the CPU in your computer, right? Now, V is your storage. For us, this is a vector database, and the example that I'm going to give is obviously Notice. And this can be the storage for your CPU, for your CVP framework. And finally, P is prompt as code, which is the interface. How do you interface with your computer, right? It's through some sort of software, through some sort of code. And that's what prompt as code is really going to be. Okay, so the application that we built to showcase this, and you can see it in my little tabs over there, is called OSS Chat. And OSS Chat is a way for you to interface with an existing open source software application and ask it questions, and it will give you the right answers. And later on, I will show you how ChatGPT gives you some of the wrong answers. I'm going to cover this architecture very briefly. And I'm going to stop after I cover it very briefly to see if anybody has any questions, okay? So the first thing that you need to do in order to get domain-specific knowledge is that you need the actual text. So we get the information from GitHub or from Docs, and we chunk this up, and we get the we get the embeddings, the vector embeddings, which I'll talk more about later. And this architecture diagram actually skips a step. We actually take these, take the chunks of text, and we go to ChatGPT and we say, hey, here's some information. What are some questions that I would ask that would result in someone telling me about, this information? What kind of projects can I create with LangChain, for example? Who knows what LangChain is? Ah, okay. Hey, you want to tell me what LangChain is? Yeah.
So we connect different large language models together and have tools that work out of the box between them.
Cool. I think that sounds about right. Some of you want to pass these socks back. I definitely can't throw that far. I'm going to pass these to you. Can you pass this back to that guy over there? That guy right there. Yeah. Okay. So after we generate some of these questions, then we have the question embeddings, and then we also get the answer embeddings. The answer embeddings from the docs, the questions embeddings from ChatGPT. Once we have these, we store them in a vector database like Milvus or Zillas Cloud, which is the commercialized version of Milvus. And in OSS Chat, you can ask questions about this open source software. And then when you ask it a question, instead of going straight to the LLM, instead of going straight to ChatGPT and getting a wrong answer, what it does is it first checks the database. It does a vector search. This is what I'm going to talk more about later. And it says, okay, let me find the most similar answer to what you just asked. And then I'm going to grab the answer to that question. Oh, sorry, let me find the most similar question to what you just asked. Then I'm going to grab the answer to that question. I'm going to send that to ChatGPT. And then ChatGPT is going to send that back in a chat interface response. Okay, does anybody have any questions about what I just said? Yes.
So when you're looking for similarity between questions, you just create a distance between the two vectors of the questions?
Great question. So you said if you're looking for similarity, is it just Euclidean distance? It can be, but it can also be cosine similarity, the inner product, or the Manhattan distance. But nobody really uses Manhattan distance, so it's mostly L2 or inner product. Sasha?
In terms of performance, how much of a boost do you get compared to like asking ChatGPT to check its own code or something like this?
In terms of performance, like speed, like latency?
Like accuracy or
Oh, accuracy. Well, actually, you'll see this in a second, but ChatGPT has no idea what LangChain is. So 100%, I guess.
You can use Bing though, because Bing is connected to the internet, so you can use ChatGPT for it through Bing and it knows what it is.
Okay, well, I'm gonna show the example later anyway. Yes, question.
Second question was, when you have a question and you look for similarity, like, how do you know that the question is similar enough that the answer is correct?
You have to use some sort of, a cutoff in terms of like similarity, yes. I think someone else had it, yes.
Sort of piggybacking on his question, when you have similarity between questions, do you curate the answers to make sure whatever question was asked is actually useful? Because effectively you can have a similar question that was gone to ChatGPT with the same embeddings, but as a result it's garbage, and you get similar questions with garbage results. Does that make sense?
Let me repeat this back to you. So if ChatGPT generates garbage questions from my docs that I get it, and I ask a question that is similar to one of the questions that ChatGPT generated that was wrong, does it still return the answer? Yes, because this thing cannot think, it is a software. Yes.
What about cold start when you don't have any questions yet? How do you build up your questions database?
Yes, so the questions database is actually built from the docs. So what happens is the docs are chunked, and those doc chunks are sent to ChatGPT to create the questions for you. So ChatGPT is able to look at some sort of like text and generate like questions that would make sense to ask to that text would be an answer to. Okay. Yes?
What's the normal vector for different dimensions?
What is normal vector dimensions? That depends entirely on what your data is. I think the default that we have in Notice is, I want to say it's 384. Don't quote me because I do not completely remember. Yes.
So if you give a doc to ChatGPT and ChatGPT generates a question, how accurate is if you immediately ask that question to ChatGPT? Do you get the same doc back, or?
You mean if I ask it to ChatGPT with the vector database in the CVP framework, or if I just ask ChatGPT with
The same question.
if I just ask ChatGPT, like on OpenAI?
Yeah.
It's not going to work because ChatGPT has no context. Okay. Oh, one more. Okay, and then I'm going to move on. You, yes. Did you raise your hand?
Okay. Do you need to train the embedded pipeline in your domain, or like telling what is similar in your domain and what is not similar?
That is a great question. So you have to use a model that is trained to be able to formulate these questions. So it does, like the model that you generate the vector embeddings from does matter. Yes, you can't, like, I can't go in and use like an image model and expect to get the correct vector embeddings, but if I use a text model, I would expect it to get the correct vector embeddings. So for example, I could use sentence transformers, but probably not less than 50. Okay, I'm gonna move on. If you have more questions, please ask me at the end. Okay, so now I'm gonna show you the correct response to this hallucination. How do I perform a query using Milvus? So I said earlier that the real way to use this is you use a function called connections from the PyMilvus library. So you notice that the imports here are different, and the actual line that I outlined in red is different. It uses connections.connect. The host and the port is still the same. But this is the response from OSS chat with the domain-specific knowledge. Okay, so why does this work? Okay, we're gonna take a look at what semantic search is. What is semantic similarity? I think a lot of us have probably heard the word semantic before and don't really know what it means. So in the case of vector embeddings, something that is semantically similar is a close distance. So as, what's your name? as I was asking earlier, what do you use to calculate the distance between these vector embeddings? And really, there are a few different metrics for that. There's L2 or there's inner product. And there's many ways you can calculate that. But what it really means is the metric that you've chosen for your calculation is relatively close to between two vectors. And the seminal paper on this is really about, the example from the seminal paper is if you have the words king, queen, woman, and man, if you subtract woman from queen and add man, you should get king, right? This is like the meanings of the words are similar. So semantic similarity, vector embeddings, what they allow you to do is they allow you to perform math on unstructured data. And in this case, they allow you to perform math on text. Okay, and so how does this actually work in practice? Somebody has asked questions that kind of hinted at this. But as I was saying earlier, you take the knowledge base, your documents, you feed it to some sort of model. So in this case, sentence transformers, and you get the vectors from the model. Who knows which layer the vector embeddings come from? There are socks for this.
The one before last.
Hey, yeah, who said that? Okay, somebody pass these socks to him. Yep, that guy over there.
The one before last.
Yes, the one before the last, the second to last layer. So typically with neural networks, we're used to seeing things like a sort of classification or some sort of regression. In the case of text processing, we're often used to seeing things like some sort of thing like NER, like name entity recognition. But what these models are really doing is they're taking this like large set of numbers, and they're using these numbers to represent your input. And these numbers, this large set of numbers that represents one input, is called a vector, or a vector embedding. And so what we do is we chop off the last layer, and we grab all these numbers, the vector embedding, and then we stuff it into a vector database, in this case, notes. Okay, so what is a vector database? I think that by this point, you guys probably guessed that vector databases are databases that are used to hold vectors. But the definition that we like is a database purpose-built to store, index, and query large quantities of vector embeddings. And there's the GitHub link again, if you've forgotten it. And why do you need a purpose-built vector database? So I see this question online all the time. So who knows what PG vector is? Yeah, okay. Do you have socks already? You?
No.
No, okay. What is PG vector?
Postgres extension to support vectors.
Indeed, okay. Let's see if I can throw this far. Nice, okay. So why use a purpose-built vector database instead of something like PG vector or FACE or HNSW? If you've heard of any of these things, good for you. If you haven't, I'm going to cover them. Both the vector search library and the vector database allow you high-performance vector search. Really important, right? But things that a vector database has that these vector search libraries don't have are things that you would expect some sort of database to have, right? Replication, failover, scalability. Especially in the cloud, as you reach billions and billions of vectors, you're going to need scalability, and that's where having some sort of distributed system backend comes into play. And if you know how to build those yourselves, congratulations. If you want to build them yourselves, I'm sorry. And so vector databases also come with indexing, backup, recovery, really, being able to handle a high amount of insertions, a high amount of queries. And recently, NVIDIA has actually integrated with us to provide GPU support. So, now Milvus is also hardware accelerated, and Milvus does billion scale storage. Okay, so so now I'm going to cover some things like vector indexes and kind of like what is a vector database doing behind the scenes? Like how is it really leveraging these different technologies and algorithms to find your data? Because if you have a billion vectors and you just brute force search a billion vectors, you do a calculation on all of those vectors for how far it is, like in any distance, L2 or inner product, you're going to be sitting there for hours. So how does this actually work? We use some sort of thing called a vector index. And I'm not going to dive too deep into what vector indexes are and how you choose them, but I'm going to go over a couple of them. So this one's really popular. It's called Annoy. approximate nearest neighbors, oh yeah. Spotify came up with this, I didn't come up with this name. And so the way this works is basically you take your vector space and, we're not really working with a two-dimensional space, but imagine that you have a 1,000-dimensional space here and you split it in half. And you split it again and again and again and again and again. Until you can't split it in half anymore. Well, not really, but until you get to a small amount where you can say, okay, here's my vector, which one of these cluster segments does it go in? And so Annoy ends up with something that kind of looks like that last image on the, what direction is that? Right there, that looks kind of like that. And that is one way you can do a vector embedding, and that makes your search a bit faster, or a vector index that makes your search a bit faster. And there's also inverted file index. So this is pretty popular. And what this does is it clusters your vectors into centroids. And once you have all these centroids, you throw in the query vector that you're looking for. And the first thing it does is it says, which one of these centroids is the closest? And then it goes into that centroids cluster and it compares to those vectors, right? So that's a lot faster than just comparing to all of the vectors, right? And now I'm actually going to introduce you to an even more fancy one called Hierarchical Navigable Small Worlds, HNSW, because nobody wants to pronounce the whole name. So the way this works is actually kind of like IDF, right? So you start out with a sparse representation of your vectors, and you look for the closest vector to the vector that you're querying with. And as you go down into the layers, you get into a denser and denser set of vectors, much like the way that IDF works, except you're kind of abstracting out some of the brute force. Okay, so that's pretty much all there is for the vector indexing. I'm going to talk very briefly about Milvus architecture and what it means to be a distributed, to have a distributed system native architecture, right? So Milvus starts off with, I'll do it from this angle, okay. Starts off with the SDK, this is how you interact with it, right? And then as you go down, you're sending it to some sort of load balancers, you have some sort of proxies, don't worry about this stuff too much. Gets into the message storage, which actually Kafka and Pulsar, if you guys know what those are the streaming services that we send data with. And this is the important part, okay? There are 3 different nodes that Milvus uses. Many other vector databases use one node or one type of node to do both, to do all 3 things: indexing, querying, and data. And so this is what really sets it apart. Is we have 3 different nodes for this, and the data node, as you may predict, handles the data. You use it to basically query the data, it loads the data, it holds the data before it gets put into S3. S3 is just our example of permanent storage. I don't know, Azure has its own thing, so I know we're Microsoft. And then the query node does the querying for you. So you use it to actually perform the calculations that you need to do the vector querying. And the index node does the indexing. And so I'm going to tell you a secret. I don't actually know if this is publicly released, but this is really cool. The index node is actually shared among all of the instances on Zillas. And this is because indexing is done very, very rarely, and having an index node is pretty wasteful. Unless you're re-indexing your data, in which case you're probably using a vector database wrong. And so one other thing that's really cool is that Milvus stores everything in 512 megabyte chunks. So who has a guess at how much data you normally expect to work with when you're working at this scale in terms of like bytes? There's a sock. It doesn't matter if you're wrong. Okay. So normally you'll be looking at like hundreds of gigabytes, maybe up to a terabyte of data. And if you want to query a terabyte of data, you're going to be sitting there for a very long time. So what Milvus does is it splits them into 512 megabyte chunks, and it queries everything in parallel. So that's Milvus, that's a vector database. Do I have time for a quick demo, like 5 minutes, 10 minutes? Okay, cool. So I'm going to go over a quick demo. So I'm going to go to ChatGPT first, and we're going to ask ChatGPT about LangChain and what it can do. Wow, okay, so this is not the response I expected, but this is equally bad. Yeah, ChatGPT doesn't know what LangChain is. So the last time I asked it about LangChain, it gave me a response on a blockchain thing, and that's also incorrect. Actually, I think that was a real project from like I want to say 2017, but not really sure. Now, if I go to OSS chat, which includes, LangChain, there it is. Includes information about LangChain. Hopefully it gives me the right answer here. There you go. So LangChain can be used to build, to answer questions over specific documents, chatbots, and generative models. However, LangChain's flexible tool can be used for many other applications as well. Yes, question.
Now, earlier you said you had text that was chunked up and questions were generated from it. So is this answer a predetermined answer, or is it a generated answer from your data?
Why don't we find out? Looks like it's pre-recorded, pre-made. Yeah. Yes, and then what else was I going to ask it? Or really, I was just going to ask it about LangChain. So that's pretty much all I've got for now. That's OSS chat. Okay, so yeah, my name is Yujian Tang. I'm from Zillas. If you want to check out the vector database Milvis, go to GitHub, check us out. That's the same QR code from earlier, so it doesn't work. This looks like you have a question.
So how do you deal with the new data that is being generated? So how do you keep on running your pipeline and training that with basically populating new data in your pipeline?
How do we populate new data into the database?
Yeah.
Right. So, like I was saying earlier, one of the advantages of Milvis is that it has these 512 megabyte chunks, and you can continuously add to these chunks, and actually called segments. Segments, and you can continuously add to these segments, and it won't. There's two ways to index it, and number one is you call a function called flush, and flush indexes all of your new data. Or number two is what actually happens is that when the data is less than 50 megabytes, we just brute force search it.
No, I'm asking about how do we get new data into the system? Not what we enter, but in the back end, how do you integrate new data and how do you store it?
Let me see. Okay, so you mean because new data gets generated, how do I add the new data into the vector database?
Yeah.
Okay. Pretty much the way that you would pipe data anywhere, you use some sort of data pipeline. Either you set it up and you have it trigger on events, and every time you update your docs, it'll update, or you just manually add it in. Yes.
So we have a large corpus of public data, and then we have a small corpus of private data from customer. So we want to build a model with a large corpus of public data and additively add the private data. Can we do that?
You have a large corpus of public data and a small corpus of private data. And you said build a model with large data, like a LLM or like a?
We want to use an architecture like this, but we want to segregate it. So the answer coming back, if you're from a private source, it's going to be different potentially than from the public source. But every single private source would have a slightly different answer.
Yes, you can do that. So Milvis has these things called collections, which are basically I guess you can think of it like a table in a SQL database where you can query that collection or that table.
So
Yes.
Do you use OpenAI's embeddings to construct the vector database?
You mean, do we use the OpenAI's embeddings to construct the vectors and put those vectors into the database?
Yeah.
You can. It's actually up to you. You can use whatever model you want. Actually, we have a library that does it. It's called Towhee, Towhee. As you can tell, we like birds. But you can use whatever model you want to get vector embeddings.